Hi everyone, today we're going to be going over exam FM, specifically topic 2 annuities. This is actually a pretty important topic because it lays the groundwork and the foundation for even loans and uh, bonds and all these other topics, even in topic 5. So this is actually a pretty important topic that we're going to be going over today, which are annuities. Annuities, the base of annuities is that these are regular payments that occur repeatedly over like a fixed interval. So, for example, every year or every quarter, every month, or every couple years, having a fixed payment over a long period of time. That's what we call. That's what's known as annuities. And there's two types of annuities: annuity immediate and annuity due. Annuity immediate starts at immediately after or immediately one term, but one term before the first payment. So as you can see, A5I, that represents the present value of the annuity immediate, and then S5I represents the accumulated at the end of the annuity. So annuity immediate goes from one term prior to the first payment date to immediately after the last payment. On the other hand, annuity due starts immediately after the first payment, and then it goes until one period after the last payment. And so there's a lot of different relationships that it's important for us to understand the how to go from annuity immediate to annuity due, and the how you go about doing that is just by multiplying by the interest rate. So in this case, going from time 3 to time 4, how do we get from A5I to A5I annuity due? We just multiply by the interest rate. And same thing by going backward, time 4 to time 3, we discount. And then, so for example, and then another thing, present value at time 6, if we want to calculate present value at time 6, we simply multiply by the interest rate, right, 3 times. For if we're starting from annuity immediate. If we're starting from the present value of annuity due, then we simply multiply by 1 plus I twice. So that's how you get to present value at time 6. And we can also go by doing the accumulated value of 3 payments and add that to the present value of 2 payments, right? So if we have 3 payments, right, that's over here. Time value 6 was over here, right? That's the accumulated value of the 3 payments, right? This is the annuity accumulated value of the annuity immediate for 3 payments, and then we add that, right? So that's this, and then we also have to take into account this, right? So this is the annuity immediate for 2 payments. And so we add those, that's how we get to present value at time value 6. So 6. So these are just different ways of calculating the present value at time equals 6. Annuity 5, due annuity 5 is also equal to the annuity immediate of 4 payments plus 1. So a way to visualize this, and a lot of this is actually based upon visualization and just drawing out where your annuities are, where the payments are in the payment structure. So for example, for A5, that's annuity due, the present value of an annuity due, 5 payments, right? That is this at time 4. Now this is equal to if it's an annuity immediate with 4 payments plus an additional 1, right? So if we can see this at time 4, what I circled in blue, that represents 2 things. That represents the annuity, annuity immediate with 4 payments and annuity due with 5 payments. And so the difference between that is if we just add a 1, right? If we just add a 1 to our annuity immediate, then we get our with 4 payments, we get our annuity due with 5 payments. And so that's the relationship that we also need to understand. And then another thing is if we have 3A5, that's essentially saying that, hey, we have a present value of the annuity immediate at at five payments. So at time 3, that's the present value. We go back 3. So right, 1, 2, 3, right? We go back 3. So we're talking about what's the present value here? What's the value here? Right? Then how do we calculate that? So this is essentially A5, right? Discounted 3 years, right? In the past. Now, how do we calculate this? Well, that's the same thing as the annuity immediate of 8 payments. So 1, 2, 3, 4, 5, 6, 7, 8, right? But then we have to subtract this amount. And what is this amount? This amount is the accumulative of the present value of an annuity with 3 payments. So that's A3. So if we just subtract this, right, this annuity, this 8 payment annuity immediate with this 3 payment annuity immediate, then we get our A5 discounted back 3 years. So that's another important relationship that we need to understand. And then how can we calculate this? So like, what's the formulaic representation for this? Well, one way we can derive this is through geometric sequence. So how do we calculate the accumulated value, or the present, not the accumulated value, but the present value of these 5 payments? So we're over here. Okay, well, we have 4. At time 4, we discount 1 year, so that's v. Then we add v squared, then we add v cubed, v4, v5. Right? It is just representing the number of years that we're discounting by. So at 5, we're discounting 2 years, 6, 3 years, 7, 4 years, 8, 5 years, and so on, right? So, and the formula here you want to remember is that the sum of the geometric sequence is the first term minus the first omitted term over 1 minus the common ratio. And this is, again, even if you don't remember the formula, even if you just remember this formula for geometric sequence, you can find the pattern of the geometric sequence and then just apply the formula instead of memorizing what the generic formula actually is. So you could just remember that, okay, geometric sequence is the first term minus the first omitted over 1 minus the common ratio, and you could just apply that instead of memorizing this specific formula. So in this case, right, first term is v minus the first omitted term is v to the 6 over 1 minus the common ratio, which is v. And then we simplify that and we get this, and then generalize that, then we get this formula over here. And then same thing for accumulated of 5 payments, right? Again, it's just accumulated 5 payments, so we're at 8. So the first, it's just the payment at 8 is just there, right? There's no interest. We're not accounting for interest there. But the 7, we're accumulating interest for 1 year, 6 2 years, 5 3 years, and finally 4 4 years, right? So then we have 0, right? That's 8. That's at 8. 7 at 1, 6 at 2, 5 at 3, and 4 at 4. So again, we can apply a similar formula here, and then we generalize it, and we get this is the formula here. And then now the payments can also be perpetual, right? There can be ongoing forever and ever. So what we call perpetuity. And the formula for this, you could just memorize this, is that it's 1 over I. It's 1 over I. So let's dive into what that actually means. So let's say you're starting at time 0 and you're paying a payment of $1 for forever, right? It continues forever, 1 2 3 on and on. And so what's the present value of that annuity immediate? It's 1 over I. It's 1 over I. Now what's the present value of the annuity due? Well, it's 1 plus the present value of the annuity immediate. And why is this the case? Well, let's take an example. And this is similar to the logic that we described over here, right? But let's take a look at an example. So this you can think of this, what we have here, as the annuity due. Present value of the annuity due, or the perpetuity due, not perpetuity due. So then how do we make sure that we're calculating the correct annuity due and annuity immediate? So this is the perpetuity due, right? And by annuity, I meant perpetuity, because it's an infinite amount, right? It's an infinite amount. So that's what I mean. So when we have 1 1 1 1 1, right, forever, how can we calculate this perpetuity due? It's adding 1 to the perpetuity immediate. So let's say we have 1 1 1. Now, if this was actually the perpetuity immediate, then only these would be 1, right? The first time that wouldn't count because it's 1 term before. So then how can we get from this perpetuity immediate to this perpetuity due? Is simply by just adding this 1, right? And this is similar to what the concept that we went over before in this example, right? Where we're adding just 1 to the payment amount. So by visualization, you can really identify the difference between, and go back and forth between annuity immediate, perpetuity immediate, and perpetuity due. And so now we go into the idea that, okay, now we have all of these different variables. Now we're solving equations. What do we do when we get to the point where the number of payments is actually a non-integer? So if it's like 6, we get to a point where it's like 15.7 or 14.3. How, like, where does that, because it's right, you can't have like 0.3 payments or whatever, right? It's payments are only integers. So what do we do when we get to this point of the payment being a non-integer? Well, there's 3 different approaches. The first approach is what we call a balloon payment, and that's essentially paying the amount at the floor of the number. So let's say if we get to 14.7, then we pay the amount at n equals 14. And so again, how do we calculate that? Same thing. We just discount it back to the present value, set up our equation, make sure we're comparing at the same comparison date, and then we are able to calculate the balloon payment. The drop payment is similar, but it's except we take the ceiling of that number. So it's 14.2, we go to 15. What would be the payment that we would do at 15? If we were going to pay at 15. So balloon payment, drop payment, and then the mixture payment is like, okay, if there was a 15.2 payment date, or like a payment number, right? What would the amount be at that point? What would the amount be at that point? And you can calculate this through the way that you calculated balloon or drop payment, or you can accumulate balloon or discount drop in order to get the same amount. And now we go to this idea that, hey, throughout a time period, let's say 0 to 10, there might be some cases where payment, the time when we do a payment, or the sixth payment, seventh payment, eighth payment, or even the year, the interest rate within the year might differ. And so if we're discounting, how do we take into that into consideration? So if we have like 0 to 10, right? Let's say for the first like 3 years, the interest rate's like 4%. Then for the last like whatever, like 6 years or whatever, it's like 5%, right? So then how do we discount? So if our present value is here, or if our value is here, if we're here, how do we discount? Well, if we were discounting by year, if we were discounting, if this payment, if it was interest by year, then we change, right? Then we change. So then we go to, okay, discount 5%. Okay, discount 5%. Oh, but then the interest rate of the year changed, right? So then we discount by 4%, 4%, 4%. But then if it's by payment, then it doesn't change. If it's by payment, then we go, okay, since it was already at 5% when we're calculating this, then it's back, okay, 5%, 5%, 5%, 5%. It doesn't change, right? So that's the difference between if we're the interest rate by year and the interest rate by payment. Okay, so the next topic we want to go over is annuity payment at every moment. So this is what we call continuous annuity. So we describe, annuities. They can be things that we could be doing at every month, or every quarter, or every year, or every couple of years, right? There are fixed intervals. But what happens when it's continuous? Every single moment you're getting paid, right? Every single moment. That's what this represents. It's a constant annuity. Constant payment is being given to you at every single moment. That's a way that you can actually think about it. So what's the formula for this? Well, this is the derivation behind it, and then we can see that this is the formula for the present value of the annuity, present value of the annuity, and then this is like the accumulated value. Okay, and then now we talked about annuities, but these are level annuities. These are level annuities. A constant amount is being paid at each fixed interval. But now, what do we do happens when that changes? So now we have geometric progression with payments. So the first payment is 1, then the next payment is 1 times 1 plus k, then it's 1 times 1 plus k squared. This you have to also, to bring it back to present value, you have to account for interest, and you also have to account for the differing payments. So again, we can use the same formula that we had before, where we're using the first term minus the first omitted term over 1 minus the common ratio for the geometric sequence formula. We can use that, and that's actually how we derive the entire formula of this here. You can memorize this formula, or which I think is a bit easier, just memorizing that like basic formula, like the geometric sequence formula, and just applying that to all of these different problems. And so this is the sort of the sequence, the geometric sequence that we come up with when we're adding all of this up, right? B takes into account the interest that we're discounting by, and then the 1 plus k is the amount of factor that each payment increases by. And then another type is obviously arithmetic progression. So instead of multiplying by this common ratio, we subtract or add by a common difference. And this is the formula for that. Won't do much derivation here, but if we just remember this formula, then we can solve this problem. And then and sometimes this may seem like a lot, but that's where we can have our calculators in hand, and where we can calculate an. Okay, so, and then unit increasing annuity. So if our annuity is increasing by just 1 by a constant amount, so the difference between unit increasing annuity and just an increasing annuity in general is the amount by which it's increasing. So if you have the first payment, and that's the common difference, then that's what we call unit increasing annuity. And so, for example, if you have like 1, 2, 3, that's increasing by 1. The first payment is also 1. If you have 3, 6, 9, 12, the difference is 3. The first payment is also 3. So when the difference is equal to the first payment, that's what we call unit increasing annuity. And when P equals Q, essentially. And this is the formula for that over here. And again, remember, keep in mind that this is the present value and this is the annuity due. And then this is, again, same concept, but unit decreasing annuity, where the amount that we're decreasing by, the amount that we are decreasing by is related to Well, I mean, and I guess in this case, it's just 1098. It's just 1098 765 4321, and this is essentially the unit decreasing version of it. So you can also as I was saying, you can use this formula, or you can also use the formula above here. And this is these are just specific instances of this general formula that we talked about before. And then there's also arithmetic progression for when we have infinite number of payments, and this is the formula for that. So we have so for example, if the common difference is 3 and just 3, 6, 9, 12, it just keeps on going forever, then this is the formula for that. Now if p equals q, right? So actually in that case 3, 6, 9, 12, the p equals q equals 1, and p is actually 3, and q is 3. So then we can use this 1 over I plus 1 over I squared, which is essentially just a generalization of the above formula. And again, if you want to find annuity immediates versus annuity dues, you can use this relationship that we talked about before. Now, the J effective method is sometimes we're going to be given effective rates that are at our monthly level, that are quarterly level, yearly, 2-year, 3-year, 5-year, and sometimes the problem may require you to actually have a year annual interest rate or a 6-month. And so we can use some of the concepts we talked about in actually time value of money, and we can convert that to the rate that we actually want. And then in terms of the equation and just equalizing payments at different interest rates, right? We want to make sure the fundamental thing here is we want to make sure that we're comparing at a fixed comparison date, right? And then we're discounting all of the cash flows in the future, and then we're accumulating cash flows that have already occurred. And this actually comes up when we're talking about like which asset or like which sort of interest and which payment method is the most optimal for the borrower or the lender. And we also have continuously increasing annuities. So we talked about continuous annuities, which was this idea of, okay, payments are going to be happening like at every moment. And we talk about increasing annuities, which are the fact that, hey, payments are going to be changing. Now, if we combine those two topics and we go continuously increasing annuities, we have this formula where when we're increasing this annuity, right, 1, 2, 3, 4, and it's also happening at at every single moment. That's what's known as continuously increasing an annuity. So it takes like the two concepts we talked about above about increasing annuity. We talked about arithmetic progression, and also continuous annuities, where we talked about some time before, and we're sort of integrating that into now we have continuously increasing annuities. And this is the formula for that. Again, you could just memorize it. And this refers to the continuous annuity at level payments, right? At level payments. And then if you have a varying force of interest, you can use this formula over here. And again, we can go over how it's, I won't go over how it's derived. And then we also have block payments. Block payments are essentially, we have payments, but there's different payments at every period of time. So for 1 to 5, 6, 6 to 14, in this case, 1 to 5 it's 6, 6 to 14, 18, 15 to 22, 22. And so how do we calculate the present value of this? Well, first in this example, and let's just go over this example. In this example, we assume that everything's 13, right? We assume that from 0 to 25, everything's 13. And then as we go back, we make adjustments as we go back to get the outcome that we want. So in this example, everything's 13, that's 13A25. And then we increase our amount to 9A22, right? Why do we do that? Because the next amount, if we're going back, is 22, right? Which is 9 greater than 13. So that's the amount that we're increasing by. So in this case, so if you're just visualizing this, you can think of everything as 22, everything from 0 to 22 as 22. And then from 22 to 25, you can think of that as 13. So we're slowly inching our way closer to the end outcome, the payment pattern that we actually want. So now we go, okay, again, going backwards, what's the next payment? 6 to 14, it's 18, which is 4 less than what we already have of 22. So then we subtract -4, A14. So now all of those from 0 to 14 are going to be 14. Then we go to the next. What's the next payment structure? It's 1 to 5, which happens 6 times, which is 12 less than 18. So then we minus 12A5. So you really want to get this idea of you want to start at the end and then incrementally move your way towards the present. And then you want to make the adjustments as per the payment pattern. And then sort of another sort of style of question payment pattern you might get is repeating reverse. So this is where it's like an example like I provided right here: 1, 2, 3, 4, 3, 2, 1, 1, 2, 3, 4, 3, 2, 1. So you can get the accumulated value at at time zero. You can say you can get the accumulated value here. And there's so many different ways that you can actually calculate this. Like depending how you use the concepts I described above. But one way you can do this is by saying that, okay, so we have IA3. If we go back to what IA3 is, it's unit increasing annuities, right? This is unit increasing annuities. So 1, 2, 3, 4, we have the present value of that, which is this, and that's what, 3 payments. So in this case, it's, you can do this again, like multiple different ways. So 3 payments, so it's referring to this, present value of this, plus uh, the decreasing annuity, present value of here, right? And then it's discounted 3. So we add these two, and that's how we get our present value times 0. So again, for these problems, you really have to just break apart. If you see different patterns at different time intervals, you break apart what you know for each time interval and then bring it all to the present value. And then this is just another way to do it that I won't talk about today. And then discounted cash flow. So this sort of goes into the idea that we want to bring everything to the present value. So sum of all present values of all the cash flows. That's our net present value. So again, outflow, inflow, accumulating all of that, doing those calculations. And then IRR is the interest rate that produced the net zero value. The net zero value. So how do we equal the cash outflow? Calculating the interest rate for that. That's what we call the yield rate or the internal rate. Again, just some basic principles. Is that to borrow, obviously you want to have a lower interest rate. Lender, you want to have a higher interest rate that the borrower pays. And then reinvestment rates. So these are the common question that also comes up: is that okay? Let's say you're gaining interest as you initially have this balance, and then you're gaining interest. Then every time you gain that interest, you reinvest that into like a different bank account or something. So you're actually gaining another set, like another set of your assets are getting paid interest. So this is what we call reinvestment rates. And then reinvestment rates, varying payments, interest rates, reinvestment, yeah. And then again, this essentially works like the same way. It's just two different like timelines, right? Two different timelines that you're thinking of. And that's essentially it. And then the categorization of different annuities and automatically identifying which one is appropriate. So yeah, the entire idea of this is like anytime you see a problem, you automatically want to like have an idea of what type of annuity this is, right? It may not always give you like a description of what it is, but okay, is this an annuity immediate problem? Okay, I know this formula. I can go back to this. Is the perpetuity due, perpetuity immediate? What type of like from the payments and like these different annuities patterns that you've learned, like what type of annuity is it? Like, have I done something in the past? You want to have those types of connections that each time you see a problem. And then sometimes the yield rates, you might be solving like a quadratic formula. You might get like two different yield rates or something like that. The default is to just go with the one that's closest to 0. And essentially that's it. Like a lot of this like is, again, the more practice you do, the better you will become at this. But the main thing here is you really want to understand what type of annuity it is. What are the create a timeline of visualization of where the payments are actually getting paid. Break the maybe in a more complex problem. You may have different payment amounts. You may have different varying interest rates. You might have different patterns. You may have even different annuities, like completely. So you really want to localize those, focus on, okay, this is what I know for each type of annuity, each type of payment pattern, bring them to present value. So just break the more complex annuity into its smaller pieces, and that's how that's one of the ways you can solve the problem. So yeah, that's annuities in a nutshell. Again, very high level, and I hope you've learned a lot from this.